In this part, we'll continue with the CAN protocol broadcast logic. That is, what is the logic behind the broadcasting the CAN protocol messages and other facts that is really interesting, and it's advisable to learn this. Let's start with the CAN protocol broadcasting. So CAN bus is a broadcast type of protocol. Yes, it is a communication protocol. The communication is nothing but the broadcasting. So in what way we can tell it is a broadcasting? Say for example, if I am telling something that every nodes can listen, that every learners can listen, but whoever wants that only they can acquire the information. In the same way, not whoever the single node, but everyone can have attention on it. The same way, the can also that broadcast all the nodes can receive all transmission from other nodes. This protocol states that there is no way to send a message in just a specific node. All nodes will invariably pick up all traffic. So that's what. So again, if you consider myself and you, so there is a no way of sending a message to a specific node, to a specific guy. So I used to broadcast my message. Whoever interested, they can take. That's it. But everyone can able to listen to my message. The CAN hardware, however, provides a local filtering. So here, local filtering makes a major difference. The local filtering plays an important role to make the only respective nodes can react for the message. So that is a concept of local filtering. We'll see what will happen. Moreover, the CAN bus uses the NRZ with bit stuffing, that is non-return to zero with bit stuffing. So these are all the two concepts that you have to understand, what is local filtering and NRZ. Let's see about local filtering. So here this is a simple, see this is again in our last tutorial we have seen the CAN is a physical layer. So there is, it's an interface medium. So it's take the, say for example, if you are getting some information from the CAN bus, the information has been transmitted to the CAN controller, that is CAN protocol controller. Here we have the acceptance filtering. So what this acceptance filtering will do, it will just accept what are the data which is relevant or what are the data which is needed, then it will send to the receive buffer. So the receive buffer will process it and check whether it is a valid information or not, or whether it is a required information or not. If it is yes, and if the protocol has been obeyed, say for example there will be no bit stuffing, there will be no CRC error, there will be no checksum errors, then it will just send to the application, then application will send the acknowledgement back. So this is how it will work. And here in acceptance filtering, that is in local filtering, what will happen, let's see in deep. The concept of local distance to quantify the minimum amount of errors a query fragment contributes to any distance between the query and a data string is called local filtering. So here they have mentioned in terms of the data. Say for example, if the particular data that the concept of low pass filter, band pass filter, so filtering is nothing but whatever we want that will be taken care. So in the same way, what are the data that we want without any errors? Say for example, if I'm expecting the message ID of always, if I mapped the, say for example, if I am a master node and I am access a master node and you all acting as a slave node, and if some of, say for example, if slave A is name, if mapped as the message like 0 cross 11A, like same way B has 0 cross 11B, same way C has 0 cross 11C. If I am sending some message with the identifier of 0 cross 11A, the particular node will receive with the local filtering. The local filter only allows that only the particular message node can react, but all other nodes can come to know that what I'm transmitting. So that is what the concept of local filtering. It also leads to effective protocol rules and can speed up the verification via early termination. If there is any problem, then it will terminate early, that is the filtering will just stop the communication and it will report to the master, that is it will acknowledge the error. The CAN protocol logic, all the modules are connected to the CAN bus in the AND logic. So this is a very common stuff that you would be aware. Let's see once again, no issues with that. Mean to say that if the just one node is driving the bus to a logical zero, then all other, that is the whole bus, is state irrespective of number of nodes transmitting as logical 1. So that means the CAN protocol uses the arbitration methodology. So here the simple concept they have explained is, it is unwired. So if 0 cross 1 is 0, that's what. So the CAN standard also defines techniques such as error handling and fault confinement, added with the bit timing and clock synchronization, and the CAN bit timing calculator that is used to calculate the CAN bus parameter and register settings. So here we have the two more concepts apart from the wired logic and arbitration methodology. As you know, the arbitration methodology and the wired logic as the interlinked. Say for example, the the concept, is the lowest the lowest the number will wins the priority, say because of the AND logic. So that also we'll see in the next slide. So we have another two important parameters like bit timing and clock synchronization. Let's see about bit timing. See, the controller area network or the user specified timing parameters to sample the asynchronous bit stream and recover the block. These parameters are typically based on the frequency of the available reference oscillator. There may be several options available for the given frequency, and some of them is a looser oscillator tolerance than others. The creation of bit timing parameter to maximize the oscillator tolerance for the node for the CAN module. Okay, so the concept of this is, the overall concept is, the CAN bit timing has been a dependency with many of the parameters such as frequency, then bit stream, asynchronous bit stream and clock, then oscillator tolerance, then bit timing calculator. So this bit timing calculator is a kind of output variable. That is, bit timing is output. So calculator is that we have automation calculator also, but for this we have, these are all the inputs. So these inputs has been like specified bit stream. So even when you are opening the canalizer or Kano, you have to set some baud rate, then you have to set some clock frequency if you are allowed to do. So once, if you're not, if you're not setting, then it will take as a default one. So these are all the input that is required. So let's see here one more thing how it will be. So the calculation of the bit timing parameters require at least three inputs. One is the desired bit rate. So that's what here in this slide we have seen. So we have bit stream, asynchronous bit stream, frequency and oscillator tolerance. So tolerance is always important. So for example, if I am telling you that I can you have to complete your work in on time, like within 10 minutes, means you can take 11 minutes or 10 minutes 30 seconds. So I can tell 1 minute is a tolerance, so that means you can complete in 11 minutes also. So that is what the tolerance will be there, especially for these kind of electronic stuff. Then, so bit rate, then propagation delay, that is again comes under the tolerance. Then it's a clock frequency. So this is what the three things that we have seen: frequency, the bit stream, then the tolerance, that is the propagation delay. So the desired bit rate, which is a common across the entire bus. So bit rate should be common. That is a bit rate, as you know the definition of bit rate, the number of bits changing per second. Then an estimate propagation delay between the most distant nodes on the bus. Then the CAN module clock frequency, that is a clock frequency of the modules in the CAN, the bit stream of the sampling clock. That means it is there some calibratable value. So this is actually the calculation of the CAN bit timing. So after this, the CAN bit timing error. So what happens if there is an error in CAN bit timing? Say for example, again we have some two nodes, say two nodes. So node A has to transmit node A with the data within certain time. If not happens, then CAN bit timing error will happen. That timing error will happening because of the bit making the problem in the data. So that is what CAN bit timing error. Let's see how it will work. The calculator can report. So who will report? The CAN bit timing calculator will report the error based on the several mini conditions. Number one, the CAN clock frequency. As we have seen the inputs, we have three inputs, right? So in that, if the CAN clock frequency, it should be at least 8 times the bitrate to give the minimum 8 bits. If it not happens, if it not happens 8 bits, if it ends with 6 bits or 5 bits, then it will give the error. Then the propagation delay, it must be short enough to allow a reasonable values for the phase segments. The delay should be short enough, that is, it should be a tolerance level. If it goes beyond the tolerance level, then that's it, it will not it will throw a can bit timing error. The final one is the can, there is a bit stream. The ratio between the can clock and the bit rate must be close enough to an integer to the producer usable BRP. So if you have some so it depends on the project to project. The ratio should be normally like it should be 1:2, or maybe if it is a very close to accuracy, 1:1.5 also is possible. If it is a more tolerance, then 1:3. So if it goes beyond that, then it will gives a can bit timing error. So these are all the three parameters. So again, see, these are all the three inputs that we need to calculate the can bit timings. If any of this, say for example, if the bitrate and if the bitrate and another parameter, sorry, yeah, can clock, the bitrate and can clock ratio goes beyond, then it will throw error. If the propagation delay also, if it is not within the range, then it will throw error. Then the frequency, if the frequency is not in the range, then it will throw error. So these are all the three stuff that it's 8 times. So these are the three stuff that makes the can bit timing error, right? So I guess you got something in this. I feel it's a very new concept that even I'm also explaining now only. Okay, so one more is the error due to bus length. So this is also one thing that it's not in the list, but yes, it is also one thing that will cause you error. So this is a error due to bus length is too long. As you know, the bus length of the can, that will have another tutorial, but yes, but this will impact the can bit timing error. That's what in this slide itself we have given this. So the there is a calculator reports a warning exact bit rate, which is the the bus length is too long. For why it is happening? Because of propagation delay. So again, this one is interlinked to this. So if the, say for example, if the propagation delay is for example 0.5 or 0.4 seconds, everything is perfect, but only is the length is more. If the length of the cable is more, then the propagation delay also will become more. Instead of 0.4, it will become 0.8. So it will just throw a error of propagation delay. Then because of this propagation delay, the can bit timing error will happen. So this is a very simple understanding. I feel I just made it very simple, it's not so complex. So this is how the can bit timing error will occur. And here we have the very simple stuff of can protocol logic. So here we, the node 1 2 3, these three are transmitting. This is a start of frame, this is a, here we'll have end of frame, this is a data, this is a RTR, it's a control field, it's a RTR field, this is a, here we have a data field. So we, the node 1 is transmitting, it is transmitting from the from 1 0, then 1 1 0 0, I'm sorry, 0 1, then all are 1. Then here it's a 1 0 1 1 0 1 0 0, then 1 1 0 0 0 0 0, then all 1. So again we have 1, that is low, then high, low, high, low, then all are high. So here it will just, as you know, it is a unlogic, wired unlogic, so it will calculate 0 0 0, yes 0, then 1 1 1 1, 1 into 1 into 1 1, 0 into 0 into 0 0, then 1 into 1 into 1 1. Here 1 into 0 into 0, obviously 0, so the output will be 0. So this node has loses, it loses in the race, right? So only these two is alive now. So again 0 into 0 0, 1 into 1 1, then 1 into 1 1, then 0 into 1, it is 0. So the node 3 also eliminates. So only this node 2 will take a control. So this is how it will wins the arbitration. So it will that's what, then if you calculate, this will be the lowest number than this. So that's what, the lowest number always wins the highest priority, that is it is a priority. So this is how the AND logic will works, right? So I guess yes, you got plenty of knowledge in this tutorial. Like there is CAN protocol logic, yes, maybe you may be aware already, but the timing bit timing parameter is very important stuff that you have to understand. Then apart from that, we have given the local filtering, yes. So let's just go through this once again, this local filtering as well as CAN bit timing parameters. If you go in depth, yes, definitely you will get questions from these, as well as you can just lead others, you can teach others with these kind of new stuff, so that really you will get stuff. So in our next tutorial we'll have the CAN protocol frames. So you can just have a look on it, and let's continue with the CAN protocol frames in our next tutorial.